and renewable energy and nutrient recovery. I think I've said enough on that already. So the bottom line is we need to move from this small little graphic on the left screen here, which is where we are today, where we think of water being harvested from the environment, passing through like the urban community, and then being released as some sort of form of wastewater with contaminants into the receiving water, be it into streams, our freshwater ponds in this location, through to our estuarine and deep sea environment. These are not long-term sustainable answers. Certainly globally, you can get away with it in small communities for a long time and maybe forever, but if we're looking at this as really helping solve the international problem of water and being part of an international community, this is not a solution. So what is a solution in principle is closing the loop. So this diagram, the print is too hard to see, but the concept is simple. We can harvest some of the rainwater and some of the local groundwater. We use that in the community, we treat it locally, and we recharge our aquifers so we don't upset the native hydrology. And all the food, nutrients that we consume in our society, to a large degree, we want to recycle that nitrogen, that phosphorus, that potassium back into agriculture where it came from. So we try to move towards systems of recycle. And that has huge benefits, not only aesthetically, that the waterways become nicer to use, but the ecological services that we as society rely on, having healthy communities in the sense of the ecology is the community, we can restore those again. And it makes a much more robust system. So that's the paradigm shift. And that's the physical system, but what about the sort of sociological system? We need to think about a mind shift here as well. And this graphic, I'll let you read through it, but it's a small community in India that really have turned the system on its head. We think of the costs associated with wastewater services. It's a cost to society. Well, here's a change. Because there's value in that urine, there's value in that compost from the fecal residuals, these toilets are being built in parts of India where they pay you to go and use them, because this is in communities that don't have sanitation. And so they'll pay you because they can sell the produce, the fertilizer, the compost back to the farmers and make money. So they can not only pay for the facilities being built, but they can pay you as a user for using their service, if you like, the latrines. So let's think about that we could design systems here where, in fact, if you had a high quality yellow water or black water stream from your house that someone either collected directly or through a small decentralized collection system, they could pay you for that because there's value in that residual. That's the paradigm shift here. So what would need to be constructed? What is the local agriculture or aquaculture that might support that sort of thinking? And I know to many of you that sounds way off, but in principle, that's where we need to go to be long-term sustainable. So the solutions and the starting point here is really why I'm so excited to be part of this conversation with this community. As I said, I'm not coming here with an answer. I'm coming here with a process that can lead this community to finding its own answers. And what we use are what we call, it's a bit jargonistic, I'm sorry to say, but process-oriented tools. And I'll explain what some of those are at the moment. And then product-oriented decision support systems. So this means working with the community towards what are the products that you want. What are some of the things that are going to make this community want to look at alternative ways of managing wastewater services? So what are some of the values, like the oysters, like fertilizer? What are some of the products that are going to be useful here? So we come back to this diagram, and so when we look at a systems analysis, we need to be looking at the human health. So what are the diseases potential from this whole system? What are the organics and inorganic chemicals that may cause harm to human health? And then likewise to the environment, what are the impacts on the ecosystem? What are the economics over the lifetime of these system structures? And on-site systems might have a lifetime of 15 to 25 years. The big municipal systems, ongoing renovations, but they pipes in the ground are at least there for 50, maybe 100 years. So we need to be able to compare these apples and oranges on one system, and that's what these tools help us with. So the sorts of tools that we use are human health impact assessments. So we look at a suite of chemicals and pathogens that you might get exposed to through various routes. And human health impacts. We look at the life cycle assessment. So we look at over the whole production of, say, the pipes in the ground, how much energy was used, where the raw materials come from, how are those, the end of their life, how they recycled, and what are the energy, greenhouse gas, what are the various residuals, where do those residuals go. So we use this thing called life cycle assessment. So we use these sorts of tools to assess all the sort of elements of each of the system structures. And then on the economic side, we can use this benefit cost analysis, the BCA. So we can use those sorts of tools, and we can also use what are called life cycle costings. So we look at the costs associated through the whole production or of whatever the system components are. What is the real full lifetime economics associated with the raw materials, production, the actual selling of the widgets, and the final end point of where those components of the system go. And lastly, the technological function, which is really what I see as a huge goal in having these demonstration projects, is not only do we get information about health potentials, the environmental impacts, and the economics, but we also get an understanding of the engineering robustness of these systems. So how reliable in your hands are these alternative systems? And that's something that only can come from first-hand sort of demonstration in a community. So that's what the technological function's about. We know the warts and things associated with sewer systems, if I can put it that way. We know the sorts of things that can go wrong and the problems. We've had 100 years or more of refinement of sewer systems. But we haven't had, in essence, in modern society, very much experience in alternative sorts of systems. So we need to be getting that information. And so the sort of framework that we've developed in Sweden and used there with communities like this, and come up with community options, and what is now used in Australia. I was part of a team where the major water utilities in Australia are both wastewater and drinking water utilities. And they use this framework now, along with some other modifications of it, when they're looking at the big picture of what sort of renovations and changes in their system should they be looking at. So, they work with the community and saying, what are your objectives here? And what are the options? And then selecting what are the criteria that we're going to really use to measure the sustainability. So rather than, keep coming back to this point because I want to be clear, we're not just interested in nitrogen. I know that's the immediate problem and the immediate need to fix, and why EPA is on your back, so to speak, and why the community is suffering is about nitrogen. But it's not just about nitrogen. So we need to look at criteria that deal with a whole suite of issues here to come up with appropriate long-term solutions. And then we can screen the solutions and go through the rest of this. And it's an iterative process. It's not, although it's drawn up there as a linear process, it's an iterative type of process. And today, where are we? Well, to some degree, you've defined some of your objectives as a community. You've got subcommittees looking at various options. Not necessarily all the options, but you're starting to look at a range of options, which is great. And so where we are today is I think we still haven't probably had a good discussion about what sort of criteria you're going to compare those options against. And further screening of options, or maybe hybrids of those options. And so I'd like to work with you in thinking through some of those, potentially. And when we're talking about options, I just want to now take you to where is research at, and what's happening, particularly in the toilet scene. Okay. Now the Gates Foundation, which no doubt Bill and Melinda Gates Foundation you've heard about, they have, amongst a range of initiatives, put up what they call their Toilet Challenge. So there's some millions of dollars into water, sanitation and health. Sorry for all the acronyms, that's what the WSH stands for there. So they've put a lot of money into this area, and one of those areas within the water, sanitation and health areas is to come up with, can we redesign the toilet to be more sustainable, and particularly for developing regions, but also, quite frankly, globally. And on the right there's a bit of an old Chinese photograph, or drawing I should say, which really illustrates what's been sustainable for thousands of years in China. Is they treasured human excreta. So they managed it. They have had cities for 4,000 years of over 1 million people without massive cholera and typhoid outbreaks. Why? Because they sensibly captured your own feces, put it into agriculture, grew fish from that, harvested those fish and cooked those fish to break the pathogen cycle, and fed society. So there's an example of a sustainable solution in that part of the world at that time. Okay. The Gates Foundation are trying to come up with a toilet option that will be sustainable and cost less than 5 cents a day to operate. So that's the challenge. And there are a range of possible scenarios. I'm just not going to walk you through all of them. I'm just going to talk about 3 or 4 of those just to illustrate where research is currently at. To say that when we're looking at options here in Falmouth, clearly there are options that are off the shelf more or less today, but we should be aware of what's being developed by research just so that we can slot potentially some of these other options as they become available. So, starting with the figure on the right, I mean, one bit of bodily human dynamics is the current toilet that we sit on is actually not very appropriate. As we get older, some of you might get piles and some of you might have these other problems. It's because of the inappropriate arrangement. With us, sitting is nowhere near as good for you as squatting. Squatting is a much better, because of just the physical shape of our anatomy, is a much better way to defecate. And so the Asians have got it right, amongst other societies that use squat sort of pants. Now, I know tomorrow not many of you are going to want to go and use a squat system, but that's the rationale of that toilet diagram there. So that aside, and given that a lot of the Gates work is towards countries where squatting is accepted, and quite frankly is better for you, so some of the toilets are taking that on board. But this, Loughborough University is in the UK, in England, so here they're looking at a toilet that produces a biological charcoal. Now, biochar is one way of capturing carbon dioxide, if you like. It's organic carbon, not fully carbonized, and mixing it back into agricultural soil is shown to increase soil productivity for agriculture as well as sequester carbon dioxide. Okay? So here's a partial solution to the carbon problem as well as soil fertility and productivity. So they're looking at a toilet system that can do that by carbonizing the fecal residuals, if you like, a process that captures some of the energy, so it's a sort of, not a perpetual energy machine here, but it's an energy efficient way of carbonizing, if you like, the fecal residuals. Big diagram on the right there, which I can't expect you to see, but this is an option to basically, in Delft, in the Netherlands, this team is looking at a toilet that applies currently available technologies, which is microwaving. So you microwave material to produce what's called syngas, which is a hydrogen and carbon monoxide gas, which is captured in a fuel cell and turns that into electricity. And so here you would have your either a home toilet or a cluster of toilets supplying, if you like, the material for this microwave energy recovery system. So this is technology that is actually available in components, but is not commercially available as a package for treating human residuals at this stage. So that's what this team is working towards. Another option here from the Swiss side of things, they have this no-mix toilet. So this is a urine diversion, dry fecal solids type of toilet, commercially available. So at the front you can see, here's the pointer here, the urine goes down a separate bit of plumbing here and is captured as a yellow water stream. When you sit on this toilet and the seat pushes this little button here, this flap moves away and then fecal and paper materials then go into that back pan, and that is manually removed every few weeks as you build up enough mass. There's not a lot of fecal paper and solids in a household. It might surprise you. It takes quite some time for that to build up, and there's a little fan and in there, so it's actually less odorous, this type of toilet, than a conventional toilet. So it's taking it through a charcoal filter, so it filters the air and reduces the odors and desiccates at the same time and dries it down.